Okay, so we're back from the work group meeting. Some others are joining while they are ending their meeting, the work group meeting. So
77, okay.
Marisa, whenever you prefer, I think you can start. Everything is being recorded right now.
Okay, thank you so much, Anthony. Thank you, Charles. Thank you, Joan. Here we are. So we can start the last session. I have the privilege, the honor, and the pleasure to announce that GIREP board decided to assign the GIREP gold medal to David Sokolov. David Sokolov is not only our best friend, is one of the person who support us as much as he can, which is much more than every human person can support. He was absolutely fantastic as human point of view, but professional one is absolutely big. As president of AAPT, he helped us as much as we can, and now we have an agreement which is one of the best by means of AATPP, AA Association, American Association of Physics Teacher. I have to show you the medal that will be sent him, the gold medal, in which on one side we have GIREP, on the other side we have written the citation, which is for the valuable, unique, great work in physics education and for physics education research community and durable contribution. So I'm really honored to announce that the GIREP medal will be given to him. And I show the medal one more. Is sure that it is. If David don't have till now, please launch the video, and then I will ask Elish McLaughlin to, voila, to launch Elish McLaughlin, ask Elish McLaughlin to present the citation decided by the GIREP board.
Okay, my congratulations to you, David. We would like to read out this citation of your accolades to date. David Sokolov is a professor of physics emeritus at the University of Oregon, Eugene in Oregon. He earned his PhD in physics in the field of atomic and molecular optics at the Massachusetts Institute of Technology in 1972 under Ali Javan. For over 3 decades, he has studied physics in terms of students' conceptual understandings and developed active learning methodologies with NSF and FIPSE support, in particular, real-time physics, active learning laboratories, and interactive lecture demonstrations, which have both been published by Wiley. He has conducted numerous international, national, and local institutes and workshops to disseminate these active learning approaches with both secondary school teachers and university faculty. Since 2004, he's been part of UNESCO team presenting active learning workshops in the developing countries in a project called Active Learning in Optics and Photonics, ALOP, presented to date in 30 countries in Africa, Asia, Latin America, and Eastern Europe and Eurasia. He is a contributor to and an editor of the associated ALOP training manual. Not surprisingly, David has received many prestigious awards and recognitions to date, including the 2020 AAPT Hans Christian Ørsted Medal for his outstanding, widespread and lasting impact on the teaching of physics, 2007 AAPT Robert Millikan Award, the 2010 APS Excellent in Physics Education Award, 2011 the SPY Educator Award, 2011 Latin American Physics Education Network LAPEN Medal, 2011 and 2018 he has been awarded the Fulbright Senior Specialist Grants in Argentina and Japan. David has served as president of the APT in 2011, and he is currently a member, which I share with him, and the UPAP Commission C14 on physics education. On behalf of the entire GIREP community, we are delighted to award the 2020 GIREP Medal to David Sokoloff for his invaluable, unique and durable contributions to the physics education community. Thank you, David.
Thank you.
We need a big fanfare. We need music, David.
The video now.
Ooh.
Well done, David.
Thank you. Thank you so much.
So now, Edish, can you share the talk, the medal talk of David, and can David start?
Yeah, I think, Anthony, you can give him the power.
Yep, he can share the screen as well.
Yes, David, we can see it. Perfect.
Good.
Go ahead.
Okay, am I on? Yes.
David, you are on. You are good to go.
Okay.
We see Mount
thank
Hood.
you. Thank you, Eilish. Yes. So I want to give my very, very sincere thanks to the GIREP board, the GIREP committee, and all GIREP members for this wonderful honor. And I have to say it has been one of my great pleasures and inspirations in my life to have attended GIREP meetings over the years and interacted with attendees all over the world. And it's my heartfelt disappointment that I'm not able to share this special occasion with all of you in person today. I especially want to thank Marisa, who has been an amazingly supportive friend and colleague since I first met her one morning, early in the morning, 27 years ago at the train station in Udine, when I was there to present at one of her teacher seminars. I'm quite sure I would not be here today making this presentation and receiving this wonderful medal if not for her. So thank you, Marisa. And I'd also like to acknowledge the late Lillian McDermott. Again, I doubt that I would be here today without the inspiring work that her physics education group published beginning in the 1980s, and her friendship and professional support in the advancement of my career on a number of occasions. And we will miss her very much. Also, a big thank you to my collaborators in 34 plus years of physics education research, development, and dissemination, Priscilla Laws and Ron Thornton. And as was all, they are really the pillars supporting the materials in this talk. And as was mentioned, the activity-based physics group, of which the three of us were the principal members, received the award from the APS in 2010. And then finally, to the National Science Foundation and the US Department of Education, who supported the vast majority of the things that I've worked on over the years. So to get to my talk, here's an outline of my presentation today. I want to talk about the educational problems addressed by the topic I'm going to talk about. A review of the characteristics of active learning environments, a review of in-class interactive lecture demonstrations, and then talk about the actual subject of my presentation, home-adapted interactive lecture demonstrations, design features of them, and show you some examples, and then finally wrap up and open to your questions. So what are the problems? So students, including those planning to be teachers, come into the introductory physics course at the high school or college level with definite views, often wrong, about physics concepts based on their life experiences. And physics education research has demonstrated that the vast majority of these students will leave a traditionally taught course with the same incorrect views and little understanding of physics concepts, regardless of the skill of the instructor. So in summary, if no effort is made to engage the students in the learning process, they will not learn physics concepts. Now with the pandemic, we are faced with many learning environments that are worse than traditional. And the question becomes, are there ways that we can maintain active learning for our students, including in teacher training? So I've always loved this cartoon, but updated it a little bit with Bart Simpson, who I think many of you know, or the one with Sheldon. How can they possibly not learn from my perfectly logical, sublimely entertaining Zoom lectures? And the proposed solution is active learning environments, not replacing, but complementing more quantitative work in the physics course. So let me review for you what I mean by active learning environments. So in an active learning environment, the instructor's role is as a guide, not the authority. Students construct their knowledge from observations as much as is possible. We use a learning cycle of prediction, observation, and comparison. And this challenges the students' beliefs that they bring into the course. Collaboration with peers is encouraged because there's nothing we love better than having 2 or 3 students explain the physics to each other based on observations that they've made. And laboratory work is often used to learn basic concepts. And finally, physics education research validated active learning materials are used in all components of the course. Another cartoon that I've updated for interactive lecture demonstrations. Professor Sokoloff, may I be excused, my brain is full. But unfortunately, of course, even this is not possible in many places anymore. Certainly in the US, it's very, very rare that we have in-person classes at this time. So the question we asked 30 years ago was, can an active learning environment be created in a large or small lecture? And the answer was, up until today, yes, through the use of interactive lecture demonstrations. And there's quite a bit of evidence that that is a correct answer, that student conceptual learning can be improved by the use of interactive lecture demonstrations. But the questions right now, in this moment, are more like these. Can an active learning environment be created for students working at home? Under current constraints, can we effectively address conceptual difficulties of students who are studying to become physics teachers? And finally, can we model active learning for these teachers in training during the pandemic? Another important question, because many, at least I know the faculty at my university who are teaching online, have tried to incorporate videos of lecture demonstrations as part of their Zoom presentations. So do students learn from traditional lecture demonstrations presented live or virtually? And the answer is likely no. And this is based on the research from Eric Mazur's PER group at Harvard and others that have shown that the majority of students observing a lecture demonstration who were not first asked to make a prediction about it, were not even able to describe the result of the demonstration, let alone learn from it. So the lesson, I believe, for distance learning is simply showing a lecture demonstration or a video of one, no matter how exciting it is, will not improve learning unless the students are engaged in some way. Let me just review for you, since we're talking about interactive lecture demonstrations or something based on them, the 8 steps of the in-class interactive lecture demonstrations. Describe the demonstration and do it for the class without results displayed. Ask students to record their individual predictions on a prediction sheet. Have the class engage in small group discussions. Elicit common student predictions from the whole class. Ask each student to record their final prediction on the prediction sheet, which is collected. Carry out the demonstration and display the results. Ask a few students to describe the results and discuss them in the context of the demonstration. And students may fill out a result sheet that they can take home with them. And if appropriate, discuss analogous physical situations with different surface features. And these 8 steps are done for each of the demonstrations that make up an interactive lecture demonstration sequence. Everything you need to know about interactive lecture demonstrations, and probably even more than you'd want to know, is contained in the book, Interactive Lecture Demonstrations. And it contains student prediction and result sheets, instructor's guide, teacher preparation notes, the 8-step process suitable for framing. And you can download this entire book from a link at the Home Adapted ILD webpage. And the link to that page is in footnote 4 of my abstract. And you can find the abstract on the webinar homepage. Okay, so what about home adapted interactive lecture demonstrations? So back in March, when it became very clear that teaching was going to go online, I considered what could be done with materials that had already been developed. And the natural choice was to look at interactive lecture demonstrations and how could they be delivered during a pandemic. And the design features that I considered were, first of all, base them on the materials in the book, since many of those or most of those have been research validated. they're designed to introduce concepts or review and clarify concepts for students. They're designed to be just one of a number of at-home components of a physics course. They envision students working alone online, so there's no requirement of group work or collaboration, although these could be incorporated. And the reason for this was that the majority of people going online to teach were inexperienced with this and doing it for the first time. And I felt that the lowest common denominator was something you could immediately implement without having to worry about chat rooms and things like that. So of course, they could be modified, they could be used with chat rooms, but they don't have to be. They're designed to be used individually. And finally, since I was completely isolated and unable to go to my laboratory and get any equipment, I decided that they would be based on available multimedia. So videos, photos, graphs, and simulations for students to make their experimental observations. So what do home adapted interactive lecture demonstrations look like? So the link is right here. And again, you don't have to copy this down. It's in footnote 4 of my abstract. So if you click on this link, you go to a page that looks like this. And the page starts out with some descriptive information. And by the way, the link for the book is somewhere in here. It's right here. So that's where you can download the interactive lecture demonstration book. And then if you go down to the bottom of the page, you see that there are 26 different home ILDs. And each one of these listings is linked to one of the sets of home ILDs. So what I would like to do is to demonstrate a few of them for you to give you an idea of what they look like and how they work. So I'm going to close this. I'm going to go back to my PowerPoint. So let me start out by showing you the home adapted interactive lecture demonstration on Newton's third law. And I apologize because it seems that my cursor locks every time I go in and out of this. So I'll be quitting my PowerPoint and going back in several times. So here we are. I can click on that link and you see that immediately what comes up is a prediction sheet. And this is exactly or very similar to the prediction sheet that's in the ILD book. And in fact, the students, if they click on this link right here, are able to download a copy of the prediction sheet. And here's what that looks like. Oops. There. There's the prediction sheet that the student has, and there's the possibility for them to put their name on it. And in fact, email this to you, to the instructor, with their predictions, or at least to show that they have participated in this activity. So I'll close that for now. And so this set of ILDs is on Newton's third law. And it begins with a set of demonstrations that help students distinguish between Newton's third law and Newton's second law, because here is a situation where a force is exerted on an object. They're told that there's also friction. So there are actually 3 horizontal forces in this situation, although the friction is not shown in this diagram. And there are 3 different demonstrations envisioned. The object is being pushed so it moves at a constant velocity. The object is being pushed so that it speeds up. The object is being pushed so that it slows down. And they are asked to predict how does the force applied by the hand on the object compare to the force exerted by the object on the hand? And how does the force of the hand on the object compare to the frictional force? So those are the predictions they would make. I'm not going to ask you to do it, but at this point, you would hopefully be sitting there writing down your predictions. And then finally, you see, we come to here and it says, only after you have made all of your predictions, click here to view a video of one object being pushed by another. And so I will click, the video comes up. Speeding up and finally slowing down and coming to rest. And there are the displays of the two forces. These are two IO labs and they have force sensors on them. And then the students are asked to, oops, sorry, I lost the page. I should have gone back instead of doing what I just did. And now I lost my cursor and now I have it back again. Okay, there's the page again. The students are asked to compare their predictions to their observations and explain any differences. Let me show you one other demonstration now that I have this up again, show you one other demonstration because the rest of this set of demonstrations involves collisions between objects to look at the interactive forces between two objects when they collide. And I'm not going to go through all of them, but I'll show you demonstration 6. So in demonstration 6, it says a massive heavy cart, cart A, like a truck, is given a push so that it moves toward a light cart, cart B, like a small car that is at rest. Predict how the force of A on B, the force of the truck on the car, compares to the force FBA, the force of the small car on the heavy truck during the collision. How do the directions of the forces compare? And I'm sure you're very aware that the vast majority of students will predict that the force of the truck on the car is larger than the force of the car on the truck. Especially since this is a very asymmetrical collision. So students have made their predictions, and then it says only after you've made your prediction, click here to view a video of the situation. So I click. There's the heavy truck on the left, and there's the collision, and the two forces are displayed, and the students are able to observe that the forces are equal and opposite. Okay, so there is an example. I'm going to go back to my PowerPoint. And so this particular set of ILDs, it explores Newton's third law for an interactive pair of forces. Excuse me just a second. There we go. For an interactive pair of pairs of forces, in two situations, one where an object is pushed across a horizontal surface and one where two objects collide with each other under various circumstances. And of course, it uses videos and data collection with IO labs. So having shown you one example, let me summarize the steps of a home adapted interactive lecture demonstration. Student downloads the prediction sheet. The student reads a written description of the demonstration and may view a photo, a sketch, or a video of the apparatus. Student can record their individual predictions on the prediction sheet. Only after recording predictions, the students observe the demonstration as a video, photo, or simulation, and sees the result. The student then describes the result on the prediction sheet, compares with his or her predictions, and often answers probing questions that guide critical thinking about the result. And this procedure is followed for each of the short lecture demonstrations in the home adapted ILD sequence. So that is the procedure for home adapted ILDs. I'll say a little bit more about these in a little while. Let me show you another example that uses a different mode. So here we go. This is one on electric field, force, and potential. Again, based on the one that appears in the book, ILDs. And students are asked, they're given a situation with two positive charges, and they're asked to indicate the direction of the electric field at each of the x's. So there are 3 x's in the diagram. And after they make their prediction, they're directed to a simulation. And this is a PhET simulation. And in this PhET simulation, I can position charges. And there's actually a sensor that allows me to examine the direction of the force at any position. Some of the later demonstrations also look at potential, and there is, I can't see it because your images are covering the menu on the right side of the screen. I think you can see it. There's also a meter, I think this is it, for measuring potential at various points in this simulation. So I'm going to go back to here. So there is that example. I'm going to go back to my PowerPoint. So this one explores electric field lines and potential for various simple configurations of point charges, and it uses a PhET simulation. The next one I want to show you very briefly is image formation with lenses. Here's the prediction sheet. Again, of course, they can download a prediction sheet to fill out. The situation is, this set of demonstrations looks at student lack of understanding of the function of a lens and misconceptions about that. There's an object. There is a lens, which they're told is a thin lens. And in the first demonstration, they're asked to sketch a ray diagram and whether the image is real or virtual. And after having done the demonstrations, they can look at the actual demonstration that we use in the in-class ILD. So for example, here is the apparatus. There's an object with 2 point source light bulbs. There's a lens. And then we can see what this looks like when the light bulbs are lighted. Both light bulbs are lighted. You could put a filter in front of one of them so you can see that the light going to here is coming from the top bulb and the light from here is going to the bottom of the arrow. And so the image is located here, and it is an inverted image. And of course, if we put a piece of paper here, we would see that it's a real image because there are real points where the light is focused. This demonstration also uses a simulation. So there's this very nice Fizzlet. And in this Fizzlet, I can set up a situation which shows all or a very large collection of rays from any point on the object, and it shows where they are focused by the lens onto the image. And this is, I think, is very important, and it's why we use small light bulbs instead of using a ray box in the demonstrations, because the research on this done by Fred Goldberg many, many years ago shows that students mistakenly think in terms of two or three rays when they think of what a lens does, instead of thinking of an infinite number of rays or a cone of light incident on a lens. And that's what leads them to many of the misconceptions they have about a lens. And then finally, one last part of this demonstration, we can go to a converging lens and actually see what the ray diagram looks like. So this is very, very nice. Those are all part of the simulation. And then of course, the types of questions there is, let me just show you one more, is demonstration 2. What happens if you block half of the lens with a card? And of course, students go astray on this because they think that if you block half of the lens, you block 1 or 2 of the rays that they've drawn in the ray diagram. And therefore, their typical answer is, if you block half of the lens with a card, you lose half of the image, or you lose the entire image. There is no image. And so what the experiment looks like is this. There's a card blocking the top half of the lens. And you can see that although light is now only hitting the bottom half of the lens, it's still focused from both bulbs to both the top and the bottom of the arrow. And so there's a demonstration. Whereas if you go to the situation where let's see if I can do this, where you block half of the object, then no light from that half of the object hits the lens, and there's no image of that part of the object. Okay, so let me see how I'm doing on time. I think I have maybe about 10 or 15 more minutes. So I'll show you a few more if you'll indulge me doing that. I'll go back to my PowerPoint. Oops, that's not my PowerPoint. So this one explores student misconception about the function of a lens, forming a real image of an object, and it uses the photos of the setup with a cylindrical lens and 2 bulbs, and Fizzlet simulations of rays and ray diagram. Polarized light, I'll show you very quickly. This again, it's based on the one in the book. They're asked about a model for polarized light, and then they're asked what happens if you have unpolarized light and you rotate a polarizer in front of that light. And so this is what a diagram looks like to show them what's happening. And then there is a video. And let me, oops, where's my video? Oh, sorry, I didn't open the video. There's the video. And this video was done with 2 pieces of Polaroid from a pair of Polaroid sunglasses, because that's the only equipment I had available to me when I made them. And you see, as you rotate the Polaroid, nothing happens to the unpolarized light. But if I go to this next situation where I have 2 Polaroids, the students are able to observe that. Okay, so let me, oops. So this one, polarized light, students explore concepts of polarized light and analysis with polarizing filter, and they use videos with a flashlight and 2 Polaroids from sunglasses. And then finally, 2 more I'll do fairly quickly. Introduction to heat and temperature. So again, prediction sheet. And I'm just going to show you one demonstration from this so you can see what it looks like. Here's a demonstration where the students are told they have a piece of metal that is heated to a high temperature, and it's placed in water at room temperature. What will the graphs of temperature versus time look like for both the metal and for the water? And so what do you think the temperature of the water, what do you think the final temperature of the water in the cup will be? What do you think the final temperature of the metal will be? And so again, only after they make their predictions, they can look at the video. This one is going to take a few seconds to download, I think. Oh, maybe that was quick. Let me go back to the beginning so you can see there. I'm holding the piece of metal with a temperature probe in it, a temperature sensor. I put it in to the room temperature water. Again, these were done at home, so that's just a TV monitor connected to my computer, and I'm using vernier temperature probes and software to collect the data. Okay, so that gives you an idea of that one. And I'll just show you one last one. And that is the heat engine. And again, this is one from the book. Here is the prediction sheet. And this consists of a model of a heat engine, which is made with a glass syringe that is connected to a glass flask and a pressure probe. And there's a cold reservoir and a hot reservoir, which are both cups filled with water. And there's a 100-gram mass. And what this heat engine does is it lifts the 100-gram mass. So the demonstration describes the different parts of the cycle, and the cycle begins with the engine in the cold reservoir and the mass off the piston. So it looks like this. The mass is put on the piston. Then the flask is put into the hot reservoir. Then the mass is removed. And then the flask is put into the cold reservoir. So that's what the process looks like. And the students are asked to sketch a graph of what that looks like. And now we can go to the video after they've made their predictions. Oops, I did this wrong. I'm going to stop that because I actually have the video. That video takes too long to download. So I have the video already downloaded. And here it is. And I have to get rid of this. There's the video. You can see the mass has been placed on the heat engine, depressing the piston a little bit. I enter the volume of the system by hand. Now I'm taking the flask and putting it into the hot reservoir. Watch the mass. The mass is being lifted. I'm going to enter the new volume. Sorry, that noise is me squirming around in a chair that was noisy and I didn't bother to take the sound out. So I've entered the volume. Now I take the mass off. It's the next data point. Enter the volume. Move the working substance in the flask into the cold reservoir. Wait for it to come to equilibrium. You see that the piston is going down again. Enter the volume. Just one more step. Put the mass back on again, so that this is a cyclic process. We're back to where we started from. And in a few seconds, I'll enter the volume and you'll see that we have a closed cycle. And there it is. And so the students have actually seen a demonstration of a heat engine in operation, and they're asked to make some predictions and to describe what happened. Okay, I'm going to stop this, go back to my PowerPoint, hopefully. All right, so let me summarize with some additional notes. You've now seen pretty much an example of all the different types of strategies or the different types of multimedia that are used in these. So some additional notes. They incorporate the prediction, observation, comparison steps or components of in-class ILDs. They obviously don't include group discussion or large or small group discussion. So as I said, you could include those if you wanted to use small groups in a Zoom connection, but you don't have to do that. They're based closely on the in-class versions of these interactive lecture demonstrations. They use quality videos, photos, graphs, and simulations that substitute for live demonstrations. They're easy to implement. They're an easy to implement component for teacher preparation. And they're an active learning strategy that's easily used by new teachers immediately. In fact, over the years, even in-class ILDs are a strategy that we've found teachers are able to implement very, very quickly because they don't require much equipment. And they're fairly easy to set up and do. These require no equipment and are very, very easy to implement for new teachers. Now, they have not been research validated. I'm not teaching at the moment. I would be very happy if anybody wanted to research validate them, do some pre and post testing with students. So any projects that would study their effectiveness would be most welcome by me. And furthermore, let me give a disclaimer. These are developed since March. They have not been completely refined. So I welcome feedback to improve them. And so if you use them, please send me your impressions, your feedback, your corrections, your suggestions, whatever you like. You're of course free to use them with your students. You can set up a link to the actual demos. You don't necessarily have to go to the information page if you don't want to do that, but please use them as you wish. I apologize that they are only available in English at this point. And I am happy to help you in any way I can. So that brings me to the end of my talk. This is my son. He's not in school anymore, so he's not Zooming at this point. I feel sorry for students who are just Zooming. And I thank you for your attention. I look forward to seeing you in person at the GIREP seminar in Malta next year. And I urge you to engage your students in the learning process, even at home. And finally, let's hope and pray that we can return to a world governed by science, common sense, and decency. Thank you very much, and I welcome your questions.
Thank you, David. So since most of the participants are currently as attendees,
Yes.
In order
Thank
to
you.
ask you questions,
Ah.
they can either write in chat,
Yep.
okay, or else they can raise hand and I will be able to promote them to speak, sort of.
Okay, so let me look at chat, because I
If you
know
want,
there were some.
you can stop the screen sharing if you prefer.
Oh, yes. Okay, so let me stop the screen sharing and take that ugly picture off. Now I go to chat and
Marisa would like to, yes, Marisa, you can speak freely because you're on the panel already.
Okay, thank you so much. David, thank you for a wonderful panorama. Is widespread in many topics, and you can show clearly what means direct work by student, participation by hand and mind. So what I want to ask you is related to the phenomena that occur when students associate what happens in the lab with the graph. When you perform carried interactive lecture demonstration, you sometimes use simulation instead of experiments. So the point is that real-time work helps students in imagination reduction of the phenomena in the physics representation by means of the plot. And this is well known and important, very important point. It appeared to me that also in some of your simulation or inquiry demonstration, you count on the personal work of student to do the same imaginative reduction. So, for example, for optics, I don't believe that we have to teach that they learn how is building the image, but the many track of possible light paths, the possible light paths, the many light paths that you can show helps in finding how the image is forming.
yes.
So if on one side it was for me well known the very important imaginative reduction from experiments to graphs to plot in real-time plot, now I perceive that there is a similar phenomena using some simulation by means of tutorial, by means of such a sort of tutorials that you are able to build. Is it correct? Or is only a way to leave students to think? Is
Well,
interaction, the passage from phenomena to formalization, to developing formal thinking. This is the point.
Yes. Well, look, first of all, let me say that the interactive lecture demonstrations that we developed and the labs that we developed all used real demonstrations that, of course, in labs, the students are actually doing experiments hands-on. I agree with you that this is very important. In interactive lecture demonstrations, the students are observing in real time a demonstration and interacting with that by making predictions and by describing the demonstration. What I have here online is different, and doing a simulation, using a simulation is different. In this time of a pandemic, when we are not meeting live, the question is, what can we do that's better than just talking to students? Could this be better? As I've said, I have not done the research. I would love to do the research. I am not teaching at the moment. I don't have a group of students who I can test. I would love anybody who does. if they would do that. I see Dan McIsaac has said that he used many of these with his students this year. I'd love to speak to him about his experiences. I don't know if it's the same thing, Marisa. I suspect it isn't the same thing as actually doing the experiment, but maybe it's better than nothing. That's what I would hope. And so that's all I can say, because I haven't really researched it. And quite frankly, back in March, when I was watching my colleagues discuss in a chat group what they were going to do to suddenly be teaching online in 3 weeks, I was very disturbed by what they were saying, because I knew what they were saying was basically, we completely abandon active learning because we're looking for ways of how we can take videos of ourselves lecturing. And I thought, can something be done that will be better than that? I suspect these are better than that, but that they're not as good as materials that actually involve students doing things themselves. So I hope that answers. There are a couple of questions, Diego asked essentially the same question, so I won't try to answer that. My answer is probably not as good, but I would hope it's better than nothing. A couple of people have, Vera and Dan have said probably better than nothing. And I'm trying to see, is there another question here? I'm looking at the chat. Some people made suggestions, and again, I really would love to get your suggestions if you have experience with students. Other questions?
Yeah, David, as Dean Zollman.
Hey, Dean.
I agree that these have to be better than certainly what most of my colleagues are doing. One critical part is that the students don't look at the demonstration until they've done the prediction. In class, you have control over that.
Sure.
Here, it seems like you don't have any real control. Have I interpreted that correctly? And is there any way to change it? Yeah.
I think there are ways of controlling that. I have to say again that in some ways, this is something that you might say I slopped together. I think that would be a disservice. I think they're better than that, but you can have your opinions. But I didn't try to do that. I know it's possible to do it because I've just seen some very nice materials by Bob Teese, where he's doing ILDs online, and the students can't move on until they make predictions. So I think we could do that. Would it make a difference if that were enforced, because they could write garbage in a box and go on to the demonstration anyway? So I don't know. I mean, this is an age-old question. Even with in-class ILD, students can write nonsense on their sheet and not pay any attention to what you're doing. And the only thing that I try to do is to convince them that they will learn better by doing these things. And part of convincing them of that is testing them on these concepts, including conceptual questions on their exams, because they see a very clear relationship between actually doing the demonstrations or going through the steps and doing better on those questions. But yeah, I think that's the best answer I can give. But
yeah, let me just add, I did not mean to imply in any way that what you have done is slop. It was obviously something done quickly.
I said that, you didn't.
I know. But
I only mean that the way that this has come to fruition is a process of being forced to sit at home and use things that I have And I know ways that things could be done better, but I don't have the resources to do it. But I
Yeah.
hope that I've paid enough attention to detail that they would have bring about some improvements in the learning process. But
Yeah.
you
Well,
definitely, you didn't say
you
it.
have a remarkably well-stocked physics lab at home, so you did get a lot done.
Well, fortunately, I had a set of IO. I had an IO lab. I had videos of IO labs, and I had a pair of Polaroid sunglasses and a flashlight. That's pretty much it. Any other questions? I think we're probably out of time. So I guess I will thank everybody again for the great honor and you know, for these years. Thank you, Marisa, and everybody with GIREP for these wonderful years of wonderful meetings that I've gotten to attend, probably much more than I personally deserve to, but I've certainly appreciated it. And again, I emphasize, I look forward to seeing all of you again in person in the not too distant future.
Thank you very much. One maybe final comment from Marisa or from the local organizing committee.
Oh yes, we are all time very grateful to David for his contribution to our work. We count on him in the next future, and for sure we will meet with a glass of wine in Malta next year. I am sure. A very good glass of wine.
A bottle of wine.
Anthony, you have to provide for the bottle.
I will provide for the bottle. I assure you. A case of wine.
Let's hope for the best.
I take the opportunity to invite every participants next year in Malta. But first of all, we have to finish this webinar because there are many important questions to discuss. Tomorrow maybe we have to finish at 5:30 too, because I perceive that in more than one working group there are presentations that have to be finished to be offered, and so maybe a little time in the panel have to be saved in the tomorrow. And for that, as we have the keynote at the beginning, we can leave working group to work freely as much as they can, but not more than 5:30. It's okay for everybody. Can we do that?
They cannot reply, of course, because they are as attendees, but if there are any issues, for example, they can send on the chat.
Yes. But to leave people free to finish when they want, but before 5, and half an hour past 5 is maybe the best thing.
Yeah.
So, but I'm receiving the approval.
Yes, Tom said, okay.
Okay. So thank you to everybody. David, I have your pullover with written Oregon University here, and I'm waiting to come in Portland to find another one.
Yes, very soon, I hope.
Me too. Thank you one more, and congratulations, because
thank you.
There is a very important honor for us to give the medal to you.
Thank you so much.
Before we close, I would like to remind everyone that tomorrow we start at 2, okay, 2 p.m. And you have to use the same link for the webinar, just like you entered this webinar. Okay, so same link exactly. Thank you.
Thank you very much.
I think Irish
See
wanted
tomorrow then.
Yeah, I was just going to say as well, Anthony, that we want everybody back on tomorrow, because today was very much hearing the presentations, but we had no time for discussion. So we need everybody to come tomorrow for the discussion in all the working groups.
Yeah.
Yes,
All
that's
the
right.
links used today will work for tomorrow. Okay. Okay, that's all from my side. I'm not sure if
From our side, I think. Thank you, Anthony and John and
Thank you
Marisa
all.
and David. Thank you, all of you.
Thank you,
Take
and good evening or
Good
good
evening.
day, depending where you are.
Some of them woke up at 4:30 in the morning,
In the
they're
morning,
saying.
yeah, that's true.
Have
Okay.
Thank you.
Thank you.
Bye-bye.
a nice day.
Nice.
Bye-bye.